So we've been given that f of x is 1 over x and g of x is equal to x squared. So we're asked to find f plus g of x. So for that, f plus g of x, this is really nothing more than f of x plus g of x. Alright, so we know what f of x was equal to. That was given up here. F of x was equal to 1 over x plus our g of x, which was given here as x squared. And since we can't really do anything, they're not like terms or what have you, this is all we've got. This is our answer for f plus g of x. So we're looking to find the domain of our function f plus g of x, which we found was equal to 1 over x plus x squared. Now we're looking to find the domain of a function. The important thing here is to not look for everything that does work, but actually find anything that doesn't, and then say it's going to be every number except those. All right, so in this case we have two different pieces that could potentially offer some restrictions for us. Option 1 is this 1 over x, namely x in the denominator can cause problems. The other option is the x squared, but there's nothing that we are not allowed to raise to the second power, so this guy's okay. We don't have to worry about anything from him. Alright, but we do have to look at restrictions that we might have here for having a variable in the denominator. So remember, this fraction is also viewed as a division problem, 1 divided by x. So we want to look and see what numbers are we not allowed to divide by. And the biggest no-no here for division is that our value x cannot be equal to 0. Right, and with that being the only restriction, because again there's nothing wrong with squaring any number, positive, negative, or 0, we have to say it's all real numbers except for 0. Typically they're going to ask you for domain and interval notation. So for domain here, that means we will go from negative infinity to 0. Now remember, we want to exclude the 0, so we have our parentheses here versus a bracket, and infinities, both positive and negative, always have parentheses. But it's not just that set, it's also this numbers greater than 0. So it'll be from 0 to positive infinity. Again, we exclude the 0 with the parentheses here. This is technically not correct just yet. We need to say that it's the union of these two sets, meaning it's either the numbers less than 0 or the numbers greater than 0. The only way we can do that is to include them both with that or statement. That's a union. And this is our answer for the domain. So here we've been given f of x equals 1 over x and g of x equals x squared. Now we're asked to find f minus g of x. F minus g of x is equal to f of x minus g of x. So we know that f of x was given to be 1 over x, and g of x is given to be x squared, and this becomes 1 over x minus x squared. There's no like terms for us to combine or anything like that, so that is our f minus g of x. Right here we're looking to find the domain of our function f minus g of x, which was 1 over x minus x squared. So what we're looking for here, again, anything that would be problematic for us, anything that we're not allowed to do. That would include dividing by 0, taking the square root of a negative number, anything like that. Now with the x squared, there's no real restrictions here for this guy, so there's nothing we need to worry about here. But this x in the denominator, this could be a problem for us because that would mean it could be a division by 0. We have to watch out for that. So we know that we're not allowed to divide by 0. So here, because the x is in the denominator, we know x shouldn't be equal to 0. But there's no other numbers that we have to worry about any restrictions on. Again, we're allowed to square anything we want here, so this x squared, he's good to go as is. So our domain is everything except for the number 0. The way we're going to express that in interval notation is to say, all right, this will be from negative infinity to 0, union 0 to positive infinity. Just having the two intervals is not sufficient. You must also have the union symbol between them to indicate that it could be either one of those two sets. So either the negative infinity to 0, or, which is what the infinity or the union is going to stand for, or 0 to positive infinity. Both sets here work. So this is our answer for the domain here for f minus g of x in interval notation. Alright, here we've been given functions f of x equaling 1 over x and g of x equaling x squared, and we're asked to find f times g of x. Right, so f times g of x is nothing more than f of x times g of x, which makes this problem at least straightforward. We know f of x is equal to 1 over x, so we'll plug that guy in for our f of x here. We know g of x is equal to x squared, so we'll substitute that in here, which will leave us with 1 over x times x squared. We want to simplify this down if we can. So we've got this x in the denominator. That'll cancel out one of the x's of the x squared and leave us with a final simplified answer of 1 times x, or just x, for our answer to the problem of f times g of x. So here we're looking for the domain of f times g of x, which we found to be equal to x. So the temptation here would be to say, well, x is x, there's nothing wrong with just having good old-fashioned x. So our domain would be all real numbers. You could do this way, or you could write negative infinity to infinity. However, that would in fact be incorrect. Now, it's not incorrect for any reasons that you might think that there's some crazy little rule that you're breaking in of itself by looking at just the x. The problem is that it wasn't just x. What we really found for our f times g of x from the initial statement of the problem was 1 over x times x squared. And this is the real subtle distinction, but a very important one. You always want to look for domain based on an unsimplified form of your problem. Now, the reason for focusing here on that unsimplified form is this guy right here, this 1 over x. Even though he will eventually get canceled out with one of the x's from this x squared, he's there in the denominator in the original statement of the problem. And so we have to address the restrictions that that would pose to us, meaning that 1 over x is a division problem, 1 divided by x, and x could then potentially cause us to do something illegal, like dividing by 0, which we are not allowed to do. So x is not able to be equal to 0, which we have to specify because of that 1 over x. Again, so we have to restrict our domain to be everything but 0. So that's our negative infinity to 0, union 0 to positive infinity. And that is why people often get marked wrong for seemingly doing everything correct. It's because you have to use the unsimplified form of the problem. So that's where our answer is coming from here. Alright, here we're given f of x equals 1 over x and g of x equals x squared. We're looking to find f over g of x. So f over g of x is the same as f of x over g of x. So what we're going to do then is take our f of x equaling 1 over x and plug it in for the numerator here. Similarly with our g of x being x squared, I'm going to plug him into our denominator there. So this will give us 1 over x over, or divided by, x squared. All right, now, in and of itself, this is a perfectly legitimate expression, but it is not particularly friendly. So what we're going to do is continue to simplify this down some more. The way we're going to do this is by viewing this as a fraction over another fraction. So we're going to have this as 1 over x divided by the x squared. So when we're doing that, what this is going to give us is 1 over x, that's the numerator, divided by x squared. And of course, dividing by something we know is the same as multiplying by its reciprocal, so this will be 1 over x times the reciprocal of x squared is 1 over x squared. So when we multiply this guy out, we're left with 1 over x to the third. And that is going to be our answer for our f over g of x. Here we're trying to find the domain of our function f over g of x. We discovered that was equal to 1 over x to the third. Even if we were looking at the unsimplified form, that would just be 1 over x divided by x squared. You can look at the other video for how we come about this 1 over x cubed. But there's no additional restrictions based on the unsimplified form, so we'll look at this as just 1 over x cubed. X in the denominator is always going to be a problem for us because that's a place where a 0 could live if we don't restrict the values of x. And based on what we already know, we're not allowed to divide by 0. So that means x can't be equal to 0. But that's the only other restriction we've got here. The third power doesn't offer any additional restrictions for us. So then our domain is going to be everything but 0. So that'll be our negative infinity to 0, with parentheses around the 0 and the negative infinity, union 0 to infinity, again parentheses on both the 0 and the positive infinity, and that's it. There's no other weird mathy secret type things that are going on here. We're just not allowed to have 0 in the denominator, so that's our answer for the domain.
Alright, here we are given our function f of x equals x squared minus 3, and the function g of x equals the square root of x, and we're asked to find f composed with g of x. So now when we're talking about f composed with g of x, what this really means is f of g of x. Now, this is helpful because now what this allows us to do is just focus on smaller bits and pieces by looking at the order of operations and doing what's inside the parentheses here. So in this case, the parentheses we're going to focus on is the thing that contains the g of x, and we are going to just take and replace that g of x with what we know g of x to be equal to, which is our square root of x. So what that's going to leave us with here is f of the square root of x. All right, now we're not obviously done just yet, but that gives us our next stage of the game. So what we're going to do now is focus on f of the square root of x, which means we take this square root of x here, and we're going to plug him in for x in the f of x. So what that's going to leave us with now is the square root of x squared minus 3. Now, the square and the square root are going to cancel themselves out, and for purposes here, that'll just leave us with x minus 3 for the answer to our composition f composed with g of x.
We're looking to find the domain of f composed with g of x. This composition we found to be equal to x minus 3. So now if we're looking at this just as x minus 3, you'd be led to believe the domain would be all real numbers. There's no problem with subtracting 3 from anything, and so you conclude that our domain would be negative infinity to infinity, which if we were looking at the function x minus 3 directly would be correct. But unfortunately, in this situation, it is not. The reason this is not correct is, while we did have a function that reduced down to x minus 3, the actual function pre-simplification here was the square root of x squared minus 3. Alright, so now the slight change here, well, yes, the x and the x squared could cancel themselves out here. There is a distinction in the way the problem was initially written, and thus we have to take that into account. In fact, anytime you're looking to find the domain of a composition or any kind of combination of functions, you want to use the unsimplified form of that function for the purposes of determining the domain. So here, subtracting 3 is still not a big deal, but the fact that there's a square root, this guy being a square root does create some problems for us here. So we have to look at the limitations on square root, since it was in fact a part of the problem initially. So what that means is we have to look at restrictions on the square root of x, which we know has to be non-negative. So that means that our values of x have to be greater than or equal to 0, which means that for our domain for this function f composed with g of x, we need the function's values to be from 0 up to positive infinity. Infinity will of course get a parentheses. We are allowed to include the 0, so he'll get a bracket, and that's our domain here for this function f composed with g of x.
We're given the function f of x equals x squared minus 3, and the function g of x is equal to the square root of x, and we want to find g composed with f of x. And g composed with f of x is equal to g of f of x. All right, so this first step here helps break things down a little bit, so we get to now just focus on what's inside the parentheses, which is our f of x, which is that x squared minus 3. So that's going to go in place of the f of x in our composition. So we're now left with g of x squared minus 3. And for our next move, we're going to take that x squared minus 3 that's inside the parentheses here and place it into that function g, replacing the x. So what that gives us here is the square root of x squared minus 3. And we would simplify here if possible, but we can't go any further. We can't separate this to the square root of x squared minus the square root of 3. That doesn't work that way for radicals. So this is our final answer for g composed with f of x.
Right here we're trying to find the domain of g composed with f of x, which we found to be equal to the square root of x squared minus 3. So what we're going to do here is, like we would for any other question about finding a domain, look for values of x that don't work and say it'll be everything except those. As it stands, there's no real problem with the x squared minus 3, so things are looking pretty good there. Unfortunately, that x squared minus 3 is underneath a square root sign, and we know we're not allowed to take the square roots of a negative number, so that means that x squared minus 3 is something that we have to force to be greater than or equal to 0. Right, now this is a bit of a trickier sort of a situation to look at with an inequality. So what we're going to do is forego the inequality part of it for the time being. We're going to come back to it, so don't be alarmed about that. But right now we're just going to focus on what happens when x squared minus 3 is equal to 0. Right, this is a pretty straightforward algebraic process here. We'll add that 3 over to the other side. So we have x squared equals positive 3. So then we want to take the square root of both sides, and that'll tell us that x is equal to plus or minus the square root of 3. Alright, so those are the places where that x squared minus 3 is equal to 0. Alright, so this is going to give us a basis for finding out where x squared minus 3 is greater than or equal to 0 by allowing us to set up a sign chart using a number line. So we have our negative infinity out here to the left, positive infinity out here to the right. Here is our negative square root of 3 on that number line, and here is our positive square root of 3. So what we need to do here now is come up with some test values to test each of these three intervals. The interval from negative infinity to negative square root of 3, the interval from negative square root of 3 to radical 3, and the interval from square root of 3 to infinity. Right. Now, since we're allowed to be equal to 0, these could all potentially have brackets around the various positive and negative square roots of 3, but the infinities will always have parentheses instead. So we need to come up with a test value that we want to use for each one of these. Alright, so for the negative infinity to negative square root of 3, make the number that you pick easy to work with in terms of not giving you a lot of guesswork to do in the computational aspect of it. So rather than look at something like negative 2, which could be kind of a question mark here, I'm going to make this to be a value of negative 200. I'm going to do the same over here with the radical 3 to infinity and choose a positive 200 for my test value. And between negative square root of 3 and square root of 3, I'm going to pick good old-fashioned 0 for my values to test. But the reason I'm going to pick 0 is it makes the math really easy. What we're going to do here with each one of these is let x equal each one of these test values. So we'll start with negative 200. And then we're going to plug that negative 200 in for the x squared. So negative 200 squared minus 3 needs to be greater than or equal to 0. So when we square that negative 200, we wind up getting an answer of 40,000. And so the fact that we're going to subtract 3 from that 40,000 isn't going to change the fact that, yes, this is going to be greater than or equal to 0. So this will be 39,997, but that is greater than or equal to 0, so we are good to go. This guy is a positive, so this interval is good for us. The next item on our list here is to test what happens when x equals 0. So we put a 0 again in for our x back here, x squared minus 3. So that gives us 0 squared minus 3, and we want that to be greater than or equal to 0, but it's not looking so good since 0 squared is just 0, and 0 minus 3 is negative 3, which is not greater than or equal to 0, so we cannot use this guy. So this interval gives us a negative result, so we cannot use that interval from negative square root of 3 to square root of 3. And now we're going to look at our value of positive 200. Alright, so again we'll plug that back in for our x, so we get 200 squared minus 3, and we want that to be greater than or equal to 0. 200 squared, we already know, it's going to be the same as negative 200 squared, which is 40,000, minus 3 is 39,997, which is greater than or equal to 0. So that interval works as well. So when we're looking about stating our domain here for this function, we want the two values, or intervals, excuse me, that were positive. So that's going to be our negative infinity to negative square root of 3, and positive square root of 3 to positive infinity for our domain.
So here we have our function f of x equals x squared minus 3, and the function g of x equals the square root of x. We're asked to find f composed with f of x. Now if you'll notice, there was no mention of g in the thing that we're looking for. We just want to find f composed with f. And that tells us that g is, in fact, not necessary here. You feel free to ignore him. It's just some superfluous information for this problem. And so we're just going to focus on the f composed with f, and remember that composition means this is f of x. And so what that's going to allow us to do is take this x squared minus 3, which is equal to f of x, and we're going to substitute him in here for that f of x in the parentheses. So that means what we're really looking for now is f of x squared minus 3. And this is going to allow us now to take that x squared minus 3 and plug him in for the x in the x squared minus 3. So that gives us x squared minus 3 squared for the x guy there, and then the minus 3. So we're going to deal with the x squared minus 3 squared. So that's just going to be x squared minus 3 times another x squared minus 3, and then we have that minus 3 there tacked on at the end. All right, now we're going to switch over to a blue ink just to differentiate what's going on here. But what that simplification that we're going to do here is just multiplying things out. You can call it foiling or distribution. So we have x squared times x squared, which will give us an x to the 4th, and then the x squared times a minus 3, which will be a minus 3x squared. And we're going to do the same thing with the minus 3 in that first set of parentheses, and we'll distribute him through to everything else in the second to get another minus 3x squared and a plus 9. And then don't forget about this fellow here on the end with the other minus 3. All right, so now we just look to combine our like terms. So we've got x to the 4th, which doesn't have anything else with an x to the 4th in it, so that's going to stay the same. We have a minus 3x squared with another minus 3x squared to give us a minus 6x squared. And then we have plus 9 minus 3. 9 minus 3 is going to give us plus 6. And that's our answer here for our f composed with f of x. So our x to the 4th minus 6x squared plus 6.
We're looking to find the domain of our function f composed with f of x, and that was discovered to be x to the 4th minus 6x squared plus 6. So what we're going to try to do here is look and see what values of x don't work in our function. All right, so we know that x to the 4th is just fine as is. There's no restrictions on what we're allowed to raise to the 4th power. So then we have this minus 6x squared. There's really nothing that we are not allowed to square, and the multiplying by the negative 6 doesn't change anything. And then finally we've got this plus 6 here at the end, which is also okay for all intents and purposes with finding the domain. So that means there are no real issues that we have to worry about with our domain. So that tells us the domain of this composition, f composed with f of x, is all real numbers, which we'll write here in interval notation as negative infinity to infinity, which was nice and quick for us. Good change. Alright, so here we're given a function f of x equals x squared minus 3, and function g of x equals the square root of x, and we're asked to find g composed with g of x. Now that means that we're really looking for, when we say g composed with g of x, is g of x. Alright, so now what this will allow us to do here is focus on this g of x here, and we know that that's equal to our square root of x. So this is really g of square root of x. Right, so that means that we're going to take and put this square root of x back in for our x here inside of our g. So that gives us the square root of the square root of x. Alright, now this may seem really kind of, I don't know, daunting, if you will. It's really not that bad once we change it from radical notation into exponent notation. So the square root is represented by an x to the 1/2. Alright, so that takes care of our square root of x, and then we want the square root of that, which means we'll take that whole thing and raise to the 1/2 power. So when we're looking at a situation like we have here where we have a power raised to another power, what we're going to do is multiply those exponents together. So we've got 1/2 times 1/2, so that will give us x to the power of 1/4. And that is our answer for g composed with g of x. There's nothing really further we can do with this other than we can write it in radical notation. So instead of x to the 1/4, you could rewrite this as the 4th root of x. And there we go. Alright, here we are looking for the domain of the function g composed with g of x, which we found to be the 4th root of x. Again, with domain functions, we're looking for values that don't work, so we want to look for things like dividing by 0 or taking the square root of a negative number. Actually, any even indexed root of a negative number is bad for us. So in this case, we have 4, which is, in fact, an even number. So that means that there is a restriction on what we're allowed to have inside of that radical, which tells us that we need the x then in that case to be greater than or equal to 0. There's no additional solving of this inequality that has to take place here, so that really is just it for our domain. X values have to be greater than or equal to 0, which we will write here as 0 to infinity. The infinity will of course get a parentheses, and we are allowed to include the 0, so we'll have a bracket. And that is our domain for g composed with g of x. Alright, so we're looking here at restricting the domain of a function that isn't one-to-one, and we're doing that so that we can force the function to become one-to-one, at least artificially here. And this is done for the purposes of finding an inverse to said non-one-to-one function. In this case, we're looking at the example of f of x equals x squared minus 6x plus 10, and this just generates a nice little parabola for us. We've got it here pictured in purple on the grid. So what we want to do here is first take a look, and we can see when we draw a horizontal line through here, it does hit our graph at more than one location, thus verifying this function is not one-to-one. And so with that in mind, we've got to figure out how to break this thing apart. With these sorts of problems, it's unlikely you'll actually see one of these on your homework, or you only see these on your homework, you won't see it on an exam. The reason being is this is kind of not necessarily time consuming, but can be a bit tricky and also allows for multiple correct answers. The most straightforward way of handling these things is to look and determine where the vertex of your parabola happens to be, if this is a parabola. If it's something else, then things get a little bit trickier, but almost always for these sorts of introductory examples you'll be dealing with a parabola. Alright, so based on the graph, it looks like we're at the point 3, 1 for the x and the y coordinates. We want to verify that either using your graphing calculator by entering in this equation of y equals x squared minus 6x plus 10 and finding the vertex that way using the local min feature, or optionally you can use the formula for finding the x-coordinate of the vertex, which is negative b over 2a. In this case, b would be negative 6, so we'd have a negative 6 over 2 times our coefficient for the x squared is a 1. So we have negative times a negative is a positive. So that tells us that our x value here is going to be 6 over 2, which is a positive 3, which matches up what we thought we were going to deal with here. Alright, now to find the corresponding y coordinate, we're just going to find f of 3. So that'll be 3 squared minus 6 times 3 plus 10. Right, 3 squared is 9, 6 times 3 is 18, and so a plus 10 here. So 9 minus 18 is negative 9, plus 10 is positive 1. So that's our value for f of 3, telling us that we have a vertex at the point 3, 1, just as it appeared to be here on our graph. Now you might be thinking to yourself, well, why couldn't we have just used the graph and said it looks like it's at 3, 1, so that's our vertex? It's just because the answer is because it looks like it's at 3, 1 doesn't necessarily mean it will be at 3, 1. It may have been at 3.02. It could have been, 0.99. It could have been 1.01. We needed to verify this algebraically to be 100% certain. Right, now that we've got that, and we know that then the axis of symmetry passes through the vertex of this parabola, vertically down through this line of x equals 3. Basically now we have our choice of whether we want the left-hand portion or the right-hand portion of this parabola to be used for our purposes here of making this function. So for our domain restriction, you can choose either one. In this case, I'm going to choose the positive side here, or the more positive, I guess I should say here. This is going to be going from positive 3 to infinity, and the infinity always, of course, gets a parentheses and a 3. Here, can choose to include it. Other options would have been to go from negative infinity, to positive 3 here, using this section here to the left of our axis of symmetry. Both would be acceptable answers for a restricted domain, and then you would go on to generate your inverse function based on that restriction, regardless of which one you choose. But again, here's the domain restriction we'll choose for this particular problem. Okay, so here we're trying to find the inverse of our function f of x equals the quantity of x plus 5 cubed minus 8. So first thing we want to do is just make sure we write this in terms of x and y. So we have y equals the x plus 5 quantity cubed minus 8. So now our goal here is to solve for x. So the easiest thing to do first would be to add this 8 over to the other side. So we have y plus 8 equals the x plus 5 quantity cubed. And now we get rid of that cube by taking the cube root of both sides. So we have a cube root of y plus 8 equals x plus 5. And then for our last step, we'll subtract off that 5 over to the other side. But now that's not under the cube root. So this gives us the cube root of y plus 8 minus 5 to equal x. Now we need to just switch the x's and y's around, so we have y equals the cube root of x plus 8 minus 5, and that is our inverse function for f of x. So f inverse of x is that cube root of x plus 8 minus 5. There we go. Right, so we've got our function f of x and our inverse function f inverse of x. So f of x was the quantity x plus 5 cubed minus 8. F inverse of x was the cube root of x plus 8 minus 5. That minus 5, of course, being outside of the cube root. And so now we want to find the domain and range of each of these two functions. First, it's really important to remember that these two functions are connected, and they're connected insofar as the domain of f, to this guy, is the same as, or is equal to the range of f inverse. And conversely here, the domain of f inverse is also the same interval that's the range of f. So with that in mind, don't try to overextend your math thinking here into focusing only on f of x and figuring you have to do the domain exclusively from that and the range as well. The domain, you definitely do want to focus on f of x for its domain, but for the range we're really just going to shift over to look at the domain of f inverse. But first, our domain of f of x here. So with f of x equaling the quantity x plus 5 cubed minus 8, we want to look for things that don't work, anything that would be illegal. So adding 5 to something isn't illegal, so there's no problems there. Adding the cube to it doesn't really change anything either. The cube doesn't have any restrictions on numbers that we're allowed to raise to the third power, neither are there any restrictions from subtracting 8. So for our domain for f of x, that is going to give us all real numbers. So that is just negative infinity to infinity for the domain of f of x. Now remember, the domain of f is the range of f inverse, so we have gotten the range of f inverse for free. It is just the same thing as our domain for f, negative infinity to infinity, all real numbers. So those two fellows are connected. Alright, so now let's turn our attention over to f inverse, and that was the cube root of x plus 8. So adding 8 to anything doesn't create any problems. Cube root also doesn't offer us any room for concern because it's an odd indexed radical, which means we're allowed to take the cube root of positive numbers, negative numbers, and 0. So that part's good too, and the minus 5 doesn't create any other additional problems. So all of these guys are fine, so that means for our domain of f inverse is going to be our negative infinity to infinity. So our all real numbers here for the domain of f inverse, and f inverse's domain is the range of f, so we get that negative infinity to infinity for free as well, and that takes care of our question of range. So there we are. Okay, now we're looking to find the inverse of our function g of x equals 3x over x minus 2. So again, first thing we want to do here is just replace the g of x with a y. So we get y equals 3x over x minus 2. So now we want to solve this for x. This is a bit of an irritating process, but not too bad. First thing we want to do is take and multiply both sides by that x minus 2 to clear it out of the denominator. Alright, so we have y times that x minus 2 here to equal 3x. The denominators here would cancel out. So now we have to distribute this y through to both parts of our parentheses here. So we get xy minus 2y to equal our 3x. At this point now we just need to get everything with an x in it on one side and everything else that doesn't have an x in it on the other. So we will be subtracting off the 3x over to the left side, and while I'm at it, I'm going to go ahead and add that 2y as well. So that'll leave us with xy minus 3x to equal 2y. You could have also chosen to subtract off the xy over to the right hand side. It will give you the equivalent answer here at the end. No big deal. At this point now, on the left side, we want to factor out that common x, both here on the 3x and the x from the xy. So leave us with an x times the quantity y minus 3 to equal 2y. Then for our last step here, to get the x by itself, we're going to divide out both sides by the y minus 3. That goes away from the left side to leave us with x equals 2y over y minus 3. So now we want to switch the x's and y's around. So we get y equals 2x over x minus 3, which is our inverse function. In this case, g inverse of x is that 2x over x minus 3. Alright, so we've been given our functions g of x and g inverse of x, and we're asked to find the domain and range of both g and g inverse. First one we're going to start with is g of x, and we're going to focus on his domain here. So domains are normally dealt with by finding problem values. So in this case, our denominator of x minus 2 is going to be the potential issue that we've got here. If that's equal to 0, then we'd be allowing to divide by 0, which of course we can't do. So we find out what happens when x minus 2 is equal to 0. And that is going to occur once we add 2 to both sides when x is equal to positive 2. So that's the only value of x that we are not allowed to have in our domain. So we're going to express that by excluding that positive 2 with parentheses. So we'll go negative infinity to 2 union, again a parentheses here, 2 to infinity. Remember the parentheses indicate the 2 is not included. And so that is our domain for g of x. And the relationship between g and g inverse is such that the domain of g of x is the range of g inverse. So that means he is also negative infinity to 2 union to infinity. So that's half of our problem dealt with. Now we just need to focus on the domain of g inverse, which is that 2x over x minus 3. And again, our problem is going to occur if there's a 0 in the denominator. So we need to prevent x minus 3 from equaling 0. So when that is going to occur, we'll solve this equation by adding 3 to both sides. The problem is going to happen when x is equal to the positive 3. So that means x should not be equal to a positive 3, but everything else is okay. So that means we'll be able to go from negative infinity to positive 3, union positive 3 to infinity. Again, we'll have parentheses around both instances of the positive 3 to omit him from the domain of g inverse. And again, the domain of g inverse also tells us the range of g, so that's r negative infinity to positive 3, union 3 to positive infinity, with parentheses around everything. So again, our domain of g here, so our negative infinity 2 union 2 to infinity, is also the range of g inverse. And our domain of g inverse, negative infinity to 3 union 3 to infinity, is also the range of g. So we're looking to find the inverse of our function h of x equals 3 minus x to the fourth over 5 for our values of x greater than or equal to 0. And this restriction would suggest that the regular function 3 minus x to the fourth over 5 is not 1-to-1, which you can look at the graph and find that it isn't. They've already gone through the work of limiting what the values of x have to be for the domain, so let's just go ahead and get to work with then solving this equation for x. So first we need to replace the h of x with the y to make this a little easier to look at. So we get y equals 3 minus x to the fourth over 5. Now, at this point, if you are, let's call it, unhappy with fractions or not a big fan and would like to get rid of them at this stage, we can go ahead and do that. So we'll do that by multiplying both sides of the equation by 5. Now do remember though that this 5 has to go to both the 3 and the x to the fourth over 5. The left hand side is easy, that's just going to be 5y to equal 5 times 3 is 15 minus x to the fourth. Alright, so our next move here is going to be to subtract off that 15 from both sides. So we'll move him over to the left side to give us 5y minus 15 to equal a negative x to the fourth. Now, before we can deal with a fourth root here, which is clearly going to be necessary, before we can do that, though, we have to get rid of that negative sign that's in front of the x. This guy right here is going to be nothing but trouble for us with a fourth root. So what we're going to do now is just multiply both sides by negative 1. This isn't going to have a really huge impact. All that it winds up doing is changing the signs on everything from both sides. Again, remember to distribute this negative guy here through both parts of the left-hand side. So that'll give us a negative 5y plus 15 to equal x to the fourth. Right. Now is the opportunity to do the fourth root of both sides. So we'll have the fourth root of negative 5y plus 15 to equal just x. And with that x now solved for, we switch over our x's and y's. So we have y equals fourth root of negative 5x plus 15. Could also write that as this is 15 minus 5x inside the fourth root. It doesn't really matter. And that's our inverse function for h. So h inverse of x equals the fourth root of negative 5x plus 15. That's our answer. Alright, we're asked to find the domain and range of both h and h inverse of x. And we'll start with h of x, which is given to be 3 minus x to the fourth over 5 for values of x greater than or equal to 0. Right, now this restriction here, x greater than or equal to 0, is provided for us because the regular function of h, the 3 minus x to the fourth over 5, is not one-to-one. So that's when these restrictions will occur, or when they'll be necessary. This would be a better way of putting it. That's kind of making things more complicated, which is the bad news. The good news is, though, that the domain is then done for you. The restrictions affect the domain, therefore the domain has to follow those restrictions, meaning our domain is x values that are greater than or equal to 0, which we'll represent here as 0 to infinity. Infinities always get parentheses, but the 0 will get a bracket, and that takes care of our domain for h of x. And furthering the good news is the domain of h of x is the range of h inverse, so that is also going to be 0 to positive infinity. Alright, so 2 down, 2 to go. So now we turn our attention to h inverse of x, which is the fourth root of 15 minus 5x. You may have also written it as negative 5x plus 15, and that's fine as well. So again, we want to look for what sorts of things are problematic for us in this function here. And the big issue for us now is that even index of 4 for the radical. Any even index means that the restriction of what's inside of it has to be non-negative. So we need values of x that will make this 15 minus 5x to be greater than or equal to 0. So we're going to solve this just like we would any other basic inequality. Now, rather than subtract off the 15x, which is a perfectly legitimate maneuver, I find it easier when dealing with inequalities in particular to try and keep the coefficient of the variable positive. So I'm going to add the 5x to both sides instead to leave me with 15 is greater than or equal to 5x. We still want to solve for x, though, so we're going to next divide out both sides by 5. Now, since the 5 was a positive number, we don't have to change the direction of the inequality sign, so that leaves us with an x here on the right-hand side. And the inequality sign stays the same, and then we have 15 divided by 5 is 3 on the left side. So we have 3 is greater than or equal to x. Another way of writing that is x is less than or equal to 3. So that's going to tell us our domain, which will be values of x smaller than 3 or equal to. So we'll take that as negative infinity to positive 3. The infinity will get a parentheses, and the 3 will get a bracket. So that tells us our domain of h of x, domain of h inverse of x, and the domain of h inverse is the range of h, so that's also negative infinity to positive 3. And that takes care of our problem.